check the mic and make sure it sound right, boys.
Howdy A1 fam, Dan here. And a while back, the A1 crew got to tour Oakridge National Laboratory and see the world's fastest supercomputer. Daniel Pelfrey, Principal HPC Network Engineer, was kind enough to show us around and see their flagship supercomputer, Frontier. While on tour, Daniel shared with us what working in a supercomputer environment is like. He shared challenges that comes with HPC like scalability. He also talked through some use cases and problems that HPC solves, like weather forecasting or medical research. He basically compares supercomputing being a time machine. So come with us as we tour Oakridge National Laboratory.
Hello everyone, Tim Bertino here with the Art of Network Engineering. The team is on location here in Tennessee at the Oakridge National Laboratory. I'm joined by Senior Network Engineer of the Supercomputing Systems here at Oakridge, Daniel Pelfrey. Daniel, thank you for having us out here. This is really cool. What's the high-level mission of Oakridge? Why is Oakridge National Laboratory here?
The history of the lab starts back with the Manhattan Project. That was a very dark time in our history. As things changed, the mission changed. And throughout the Cold War, basically things shifted over to more science, more what can we do with this type of thing. Supercomputing, or just computing in general, right, is related to understanding the world around us. Everything can be explained by a mathematical model in some manner, and it's a constant work in progress, whether it's the weather, whether you're looking at materials, whether you're looking at, it has practical applications, I guess. And believe me, I'm definitely not a scientist by any stretch of the imagination. I just pick up little things, but it's very fascinating and it's exciting to be here, that you're part of something that is so impacting down the road.
So let's move forward into supercomputing. A lot of us are comfortable with enterprise networks, enterprise data centers, even some cloud. What makes a supercomputing environment different from enterprise networks, and what makes it a supercomputer?
Quite a few factors there. Most enterprises, on-prem you might have 20, maybe 100, maybe 1,000 servers. Just in terms of IP space, not just servers, but we have probably, at one point in time, we probably had 20 Class Bs of IP space in use.
Wow.
So it's the scale. You have to think about, like, in terms of your network, how many ARP entries is that? How big are your MAC address tables? You have to think about, with commodity gear, most devices are only going to have a TCAM of either 8, 16, or some power of 2, right? 32K. So you have to be very mindful about your architecture. Think about in terms of AWS, how large they are, right? So, or the types of problems that you're going to run into. Anytime we also have lots of high-speed links. I mean, we're doing our internal upgrades right now for 400 gigabit Ethernet. My team, we're in the process of upgrading basically our entire infrastructure. And as one person here, Buddy Bland put the quote, "Building airplanes in the sky." I love that reference because that's what we're constantly doing here. We're constantly upgrading the network. Every revision is just an improvement upon the previous.
So it sounds like the constant is change.
The constant is very much change, and also being able to adapt with the limitations of commodity hardware. And we're not a homogeneous environment either. Every other system is going to be some different vendor. And we have to roll with the punches and make sure everything works great. And we have to make sure our infrastructure doesn't get slammed. If you think about all those number of hosts, well, what happens if all those hosts talk to some critical service, like you say your DNS or your LDAP or something like that? You have to make sure that you don't roll your center over with the shared number. So you have to be very mindful of the design and be mindful of how things will perform.
So from a design perspective, is it you and your team's network that is tying the different components of each supercomputer together?
Absolutely.
Okay.
Absolutely.
And continuing down the design path, what does a network design look like for a supercomputing environment? We're familiar with things like 3-tier and spine and leaf. Mm-hmm. Are those a thing in a supercomputing environment?
Absolutely. You have to have some standard, and basically with our standard model, we have it such that we have somewhat of a cookie cutter solution where we can anticipate when the next system or whatever changes happen, and that design allows us to bring in the next thing. So there is a rhyme and reason to that.
Well, Daniel, thank you very much for this intro into Oakridge National Laboratory and kind of giving us a behind-the-scenes peek of what the supercomputing environment looks like. We're excited to get inside and look deeper.
I'm glad you can be here.
Back here with Daniel Pelfrey of Oakridge National Laboratory, and we're standing in front of what I'm told is a supercomputer called Frontier. Daniel, can you give us an intro into Frontier?
So Frontier is our premier system right now. It's one of the supercomputers, which is our tools for science. So this is a 1.5 exaflop system. So it's
I'm going to have to stop you there.
Okay,
Can you help us understand what an exaflop is? Because I'm going to be honest with you, it sounds like you just made it up.
Okay, so no, a flop, right, is a floating point operation, right? I mean, if you think in terms of just simple mathematics. Imagine, how many calculations can you do in your head per second? And imagine if you have, let's say, 10 million people doing that same calculation at the same time. The beauty of these types of systems is you can work on and analyze complex problems to better understand the world around us by doing calculations, doing mathematical models. And basically, with the parallelism of these systems, that allows researchers to have a better understanding of the world around us for practical applications.
So we see behind us here lots of compute nodes. We know there's storage in the room as well. How important is the networking component within Frontier?
Everything. I mean, it's networking is the backbone of everything, right? Without the network, nothing will work. So we're all used to that, right?
We are now in the room that houses the Frontier supercomputer. Daniel, I want to talk networking for a little bit.
Okay.
I'm seeing all these different racks, all of the raised covering in the ceiling. I'm seeing a lot of fiber. Are we fiber only here? Is there any copper that's going into these racks?
So it depends on the distance. If you're talking in the cabinet, that will be primarily copper. If it's going to go any distance, it should be fiber. There's a lot of power in here and a lot of electrical noise, so that's why.
Okay, and I want to think about this from a management perspective.
Okay.
I'm sure these compute nodes, these storage nodes, all have management interfaces.
Yep.
Is that something you have separate network switches that handle your management? How do you handle out of band?
So that's a very good question, and so our HPC team manages certain aspects of these systems. So that is primarily in their purview. There's an internal network and an external network. One of them is basically to the file system, to the storage, and to where they can talk amongst themselves. The out of band, that is basically the commodity Ethernet that connects back to our infrastructure so that they can talk to infrastructure stuff such as DNS, LDAP, the NFS, all the stuff that the system needs to function.
Now, one of the things we talked about earlier is that this is a very multi-vendor environment. Can you kind of talk about, from a network perspective, some of the benefits and challenges to being multi-vendor?
Oh goodness. Well, I mean, so the biggest challenge there is you're going to have different monitoring, right? You're going to have to figure out, I'm not going to be able to use the same monitoring check for this vendor as I did this vendor. Most of them are similar to the Cisco COI, but some of them are drastically different. So it depends on the vendor. It's a support functionality for training. The network team is 7 people, and of various skill sets. And so yeah, that's a documentation challenge to keep track of all that.
This is very interesting because I'm always trying, since we've been here, I've been trying to draw these parallels of how supercomputing environments are different than your traditional enterprise on-premises data center. And while there are differences, at the end of the day, it's still networking, and we have a lot of the same challenges.
It is, absolutely. It's just it's a function of scale, and it's a function of knowing where your weak spots are. You have to know where your bottlenecks are, because in your standard, let's say that you had your standard leaf and spine model, it may not apply here, because if you carried all of your VLANs back to a certain point, you would exhaust your MAC your MAC address tables. Okay. So you have to be strategic about where you have your layer 2, where you have your layer 3. Some devices have ARP limits. What happens when all those devices come on the network at the same time? Those are the types of challenges that you'll see in a very large data center.
So it sounds like requirements gathering is very paramount ahead of time.
Absolutely, absolutely.
Well, Daniel, this is all cool enough seeing it from the outside, but can we get in there and look at some networking?
Absolutely, let's go.
Let's hit it.
Yeah. All right. These are what's called slingshot Ethernet switches. So all the computes connect to all the computes, and every cabinet is interconnected to every cabinet. They all go back to a central area where it has equal cost multipath to some extent to the file system. All these interconnects allows all the computes to talk to all the computes.
Okay,
at
so
a very high rate.
This is all networking.
This is all networking. You're looking at 200 gigabit Ethernet connections, lots of them. And it makes sense when we were talking about earlier about copper. If it's short range, very close by, it's copper. If it's long range, it makes sense to go with fiber.
Now, how do you plan out the physical placement of your upstream switches?
Okay, that's a very good question. We tried to keep it as strategic as possible to figure out what's a good central location for this to come back to. And there are management areas that our team coordinated with the vendors, and there were strategic places where all of the management stuff aggregates, so that we're not messing around with this stuff. So if there's something here, our management is kept completely separate from this area as much as possible. I mean, you'll still see some 1 gig connections going back to that management area.
So Daniel, I'm seeing a combination here of traditional fiber. I'm seeing some of these hybrid cables as well. Now, is the reason there's a mix, is that because of distance? Do you do the hybrid cables for shorter distance and then the traditional fiber for longer distance?
Absolutely. There's a lot of power in this room, so you're going to have a lot of electromagnetic noise. So that's the reason. I mean, you wouldn't want to run copper through any significant length through here near the high power. Otherwise, the interference. It'd be like running. If you've heard the analogy of running Ethernet near a powerful motor, right, or an elevator motor,
right,
that would cause noise on the system.
So just to be clear, all of the networking components on these compute nodes, these are part of the compute nodes. We're just looking at the backside of them. Is that correct?
Yeah, so all the computes connect to all the switches on the backside. So it's kind of like a big backplane. So when you saw where they were putting the blades in, they connect back to all these.
This is the backplane.
This is the back. Okay. So I mean, the backplane there's the interconnect between the switches on this side and the computes on the other side. And part of this goes to storage, and part of this goes in between all the computes.
Okay.
So all these systems can basically talk to each other at a very, very low latency, high speed connection.
And what are the bandwidths that we're talking about in one of these connections?
So each one of these is 200 gigabit Ethernet.
200 gigabit Ethernet.
That's correct.
Okay.
And
so I look at the back of this rack, I see all of these connections with hybrid cables and fiber cables, and now you're talking about 200 gigabit Ethernet. How do you capacity plan, and how do you monitor that capacity?
Okay. So this is keep in mind, this is all internal to the supercomputer itself.
Okay.
So they actually have proprietary software that does that side of the house as well. So this is the internals of the system. We also have our own monitoring system that monitors and manages the other side that this system needs to be supported to support it. Again, where I was talking about our infrastructure, all the stuff that these things require in order to operate.
Okay, so you're facilitating the connectivity between the supercomputer and other services that don't live in the supercomputer.
That's correct.
So can you give us some examals? Are we talking things like DNS and DHCP? What else is out there?
DNS, NTP. Make sure everything has the correct timing. Want to make sure you have a standard syslog area where all your logs get aggregated into one point. The monitoring systems can pull all these things to check for their health, right? So,
do all those services that support Frontier live in this room as well, or are they outside?
They're outside.
Okay.
Yeah.
You need to make sure that you have redundancy built in to make sure that Frontier doesn't lose those services.
Absolutely. If you can't authenticate to the system, everything depends on infrastructure to be running. Otherwise, it will not work.
It's a blessing and a curse, right?
It is. I mean, no one ever tells you, hey, the network's passing traffic today. Great job,
yeah,
right?
Great job.
It's really neat when these folks come to us and say, hey, we're having a problem. And if you think about it, hey, this compute's having issues talking to this compute, and you just help them troubleshoot the issue. We rarely touch cables in here. Okay. There are people who that's their job to physically move. Sometimes we will help them with that. It depends on the scenario, but it's exciting. If you think about an enterprise environment, Yeah, you have a cable or troubleshoot a switch port. It's no different.
Sure.
So yeah, sure. It's just a lot of it.
Well, understanding that expertise is important is key, because I'll be honest with you, Daniel, I've run some cables before. It doesn't look like this.
Same. I've had to clean. I've had to do things I'm not proud of in an emergency, but I always go back and clean it up, or try to. Right.
Wonderful.
Yeah.
We're now in front of the Summit supercomputer.
Yeah.
Daniel, can you kind of draw some parallels or give some compare and contrast between Summit and Frontier?
Okay. Well, Summit is this is an IBM system around 200 petaflops. And this is a combination of IBM power CPUs and NVIDIA GPUs. So Frontier is the HPE system. It has AMD processors and the AMD GPUs, and is 2 exaflops.
So in comparison, when did Summit come online and become available for users versus Frontier?
So Summit came online in 2018, and it became available to users in 2019. Frontier came online in 2022 and became available to users in 2023.
And for these high-performance computing environments like Summit and like Frontier, is there a typical lifespan that you try to get out of a specific supercomputer?
That will vary. Some systems will be here for, they're usually here for 5, sometimes they might be here for 7 to 10 years, it depends.
So as far as something around a 5-year lifespan for these HPC environments, that kind of seems similar to how it's handled on the enterprise side, where a computing component, a network component, when it's built by a manufacturer, could have a lifespan of 3 to 5 to 7 years. Is that what drives the lifespan of an HPC environment?
Absolutely. You can only keep so many parts in for so long, right? And there's always bigger, faster, better things coming out all the time. So yeah, it's a constant. If you're not moving, you're going to be left behind, right?
Yeah, there is no standing still.
No, absolutely not.
Daniel, I want to focus on how these high-performance computing environments are operationalized here. I've been amazed by what we've seen here, mainly around the size and scale. Now, typically, I think it seems that large organizations find it hard to move fast, and change is hard for everyone. So how do you handle that here? Are things slow moving, or are you able to adapt, change on a dime, and move in a different direction quickly?
Okay, so that's a very good question. With surprisingly, we have our processes, right? But we also have the people who are the expertise in every manner of what we need, and we have the ability to actually turn on a dime. And especially when it comes to crunch time, around acceptance, or when there's a challenge that involves everybody getting on board, that happens very frequently.
So I want to push on that. I think it seems that it's easy for large organizations to have these different silos. Specialization is important, but sometimes when people get siloed and teams get siloed, it makes it difficult to work together and accomplish goals. How do you approach that here, and how do you work interdisciplinary?
So many of us have been here since we were, so different people have been here and have worn many hats over the years. I mean, myself, I've done systems, I've done networking, I've done a little bit of everything. So there's many people like me here. Not everybody has their specialization, but they also have cross-discipline to where, and there's also the ability where we can communicate with other people who do have that expertise when we need it. Whatever discipline you need is just literally a phone call or walking to someone to get help.
That's really refreshing to hear. It doesn't always seem to be that case, especially in large operations like this.
Yeah, but the team is everything. I mean, even amongst my team, right? I mean, I have everybody complements each other's with their strengths and weaknesses. I mean, with the areas that I'm weak at, my team is strong in, and vice versa, right? So we all support each other, and that's the same way across the division.
Oh, that's excellent to hear.
Yep.
So continuing along the team dynamics, we've seen specifically Frontier and Summit today. How large of a team does it take to maintain those systems, and how many different disciplines are there involved?
So we have like we have an HPC team, we have a clusters team, we have a cybersecurity team, we have a storage team, and we have, of course, we have an infrastructure team. And each one of these teams, they have their own specializations. Like, for example, the infrastructure team is a combination of networking, infrastructure, platforms. And even in some of the other groups, there's smaller subgroups. So some of these teams vary in size. Some of them could be 7 to 10 people. And they're supporting multi-projects, right? So it's not just Summit or Frontier. It could be the NOAA system. It could be many of the other projects that we support here.
Daniel, we've had an amazing visit today. We're a network engineering focused podcast. So we've gotten to see hands-on all of the really cool tech that's in the racks and how these systems are tied together. But I think it's important for everybody when they're working on something to understand the why. Why are you doing what it is you're doing? Can you get into some of the real world applications and benefits that the high performance computing environments as part of this lab are contributing to?
Sure, the impact is huge. Some of the things I can remember is the COVID research. They basically were doing very early analysis early on in the pandemic to help find ways of dealing with the problem. There's other things like for like the GE motor, for example, where they're basically finding more efficient ways of doing basically for power. I mean, that could also segue into battery technology, energy transfer. Of course, ultimately these systems is a time machine, right? We could use that to look towards the future to help model things. So that's why we're here.
I really like that note. You're shrinking the amount of time it would take to normally go through some of these projects. That's really cool. Well, Daniel, we thank you so much for having us on campus here. It has been amazing to learn more about high performance computing environments, especially here at the Oakridge National Laboratory. Is there any main takeaway that you would like to say about the work that you and your team do here for our audience?
Well, thanks for coming here. It's hard to quantify the impact. It's when you think about the science that goes on here and the mission and how everything happens. It's humbling to be here. It really is. So thank you again for coming in.
Well, thank you. It's been amazing to see, and we want to thank everyone here at Oakridge National Laboratory, where they are solving the big problems.
Hey team, I hope you enjoyed that video. If you did, could you give it a thumbs up and hit that follow button to keep up with new videos? And if you didn't, please let us know in the comments below what we could do better. We want to make sure our content is enjoyable and relevant, so any feedback is appreciated. Now, I personally had a lot of fun on this tour, and I want to give a big shout out to Daniel and Katie for giving us an amazing time. I also want to thank the rest of the ORNL team who made this possible. If you're interested in what they're doing at Oakridge National Laboratory and want to learn more, check out the links in the description below, and I'll see you on the next one.